Welcome back. We're just going to finish up our final remarks on these problems. Don't be afraid, you've seen all of this, almost all of this before, okay? So let's go over here a second, just take a look at what we just talked about in the last video. If we have a first order linear initial value problem, this is your standard form, and here's your ODE for a first order linear ODE, where you have completely general coefficient function here, completely general right-hand side function, some general initial condition, the value of y when evaluated at x naught is some number y naught. And based on what we talked about last time, this theorem is really the theorem that we get. It's what Picard's theorem reduces to for first order linear initial value problems. So what does that guy say? It's that as long as these two functions, p and g, are continuous on an open interval for x, right? They're functions of x, so wherever they're, as far out as you can go in x, where they're both continuous, and you pick the initial condition, the value, the x naught, you pick where you're going to assign the initial condition within that range of where both functions are continuous, then there exists a unique function, y equals f of x, explicit function, we saw it last time, that satisfies the ODE for all t in that interval, right? You're guaranteed your solution exists for that whole range, whole region, and satisfies the initial condition. Now you might say, well, that's what you might expect, but it's actually not. So that's actually a pretty cool, amazing thing about first order linear initial value problems. Based on our existence and uniqueness demonstration last time, we know that we have this solution existing uniquely throughout the entire region where the functions in the differential equation are determined how far you can go, right? So their continuity, it's in the equation. These guys determine where your solution is going to exist. So you know just by looking at the equation. That's huge because why? Let's contrast it with a first order initial value problem we've already talked about. It just has this more general form, right? Where you have some function of x and y, so it would be nonlinear in general, right? It wouldn't just be minus p of xy plus g of x, right? And what did we say? Well, as long as we had, what did the existence uniqueness theorem said there, we needed this guy in as partial derivative with respect to y to be continuous. So we found regions, right, around x naught and y naught, and how far out you could go in x and how far out you could go in y, right? That would define a rectangle around which, so my initial condition would be an initial value that would have to be both x and y coordinates within that box in order to guarantee any type of existence of a unique solution. And the continuity of this guy and his partial with respect to y help you determine that. But then what else? What are you guaranteed? You're only guaranteed existence of a unique solution for some neighborhood of x naught, right? So again, remember, where is x naught? Right, here's x naught. You don't know how far, right, to the left, so that's the right, to the right and the left you can go from x naught and still have a unique solution. You can't guarantee that you can go the entire distance where the function was, where these guys were continuous. And that's kind of like weird and crazy, right? So you can only maybe guarantee you've got a unique solution on some small region nearby, right? But you don't know what happens out beyond. So let's take a look at an example of what that would mean, okay? And so let's look at contrasting that idea with a very simple, for example, the first order initial value problem. Let's take this function f of x and y to just be something simple like y squared. That doesn't look too terrible, right? And let's just make this y at 0 equals 1. Let's look at a particular problem, okay? Now, you can solve this problem now, so let's just go ahead and solve it, right? So this guy is a first order nonlinear initial value problem because our dependent variable is y, right? It is very nonlinear. And we'll take our independent variable to be x, even if it doesn't appear here, generally x or t. So you know that means it's autonomous. Anyway, let's solve, right? So we have, using our technique of separable ODEs, we have dy dx is y squared, then dy over y squared, and separating variables is the x, yes. Now we're going to integrate, okay. What do we get on this side? Very simple, awesome, x plus a constant, right? What do we do on this side, just to make sure you guys all know what's happening here, and want to make sure, right? You got to rewrite this before you can do the integration. This is not natural log of y squared, right? You got to rewrite that as y to the negative 2 dy, right? Okay? So, it's only when we have, you know, if it was just a y, we would have a natural log. So what is this? Is just power rule for integrating, right? Add 1 to the exponent, divide by the new exponent. So add 1 to the exponent, divide by the new exponent. That's the same as multiplied by -1, right? We already have our plus c, so here we are. Yeah? Okay, now we want to, this is an implicit solution, right? Because y isn't solved for explicitly, but we can solve this guy explicitly. So let's go ahead and do that. So we have minus 1 over y is x plus c. We want to solve for y, right? And so we get minus 1 over x plus c is equal to y. Just doing the algebra there, yeah? Okay. So let's take a look at this guy. So here is, here's a solution. Right now, we won't even call this a general solution because let's look at this ODE. Can you tell me something else that's the solution of this ODE? Does this guy have an equilibrium solution? Oh, yes, indeed, right? I mean, clearly, when we divided by y, that might have given you a hint that this guy had a solution that, well, that might not possibly be in a solution we would solve for. And so y equals 0 is a solution of this ODE. It's not a solution of this initial value problem, right? Because we would need y 0 equals 0. But why, if we were just thinking about saying, oh, that's the general solution of the ODE, that wouldn't be correct because y equals 0 is also a solution which is not contained within this solution, right? Okay, so we'll just note over here. So the fact that we can say we have a general solution for these first order linear initial value problems is huge, right? We know there's not some other solution lurking out there, right? Because we showed that. All right, anyway, back over to here. Let's look at this solution here and let's solve the initial value problem now, okay? So if we're gonna do the initial value problem, then we want to do what? We're going to evaluate this guy at 0, right? So I'll just rewrite, we have y of x is minus 1 over x plus c, right? The initial condition would be y evaluated at 0. Well, what is y evaluated at 0? Well, that's plugging in 0 here, so minus 1 over c, right? What do we want y evaluated at 0 to be? We want it to be 1, right? So what do we solve for here? Nice little review. C is good, -1. Yeah? Okay. So, this guy's not part of our initial, or solution of our initial value problem. All right, so therefore, what do we know? What is our solution of this initial value problem? It is y is minus 1 over x minus 1, right? Or we could write that, if you like, without so many minuses, essentially putting the minus down here, 1 over 1 minus x. Yes? Awesome. All right, well, what does that look like, 1 over 1 minus x? Okay? 1 over 1 minus x. Well, yeah? Here's x. Here's 1, right? When x is 1, what happens? Blow up, right? Yeah? blow up, right? So as x goes to 1 from the left, look, we had to start at 0, right? We were starting at 0, that was our initial condition. So we started at 0, and as x approaches 1 from the left, what happens to the solution? So as x goes to 1 from the left, y does what? Remember, it's a little bit smaller than 1, right? So y gets huge, goes off to infinity, right? Yeah? Okay? And so y blows up, right? So the solution blows up, right? Becomes singular. At x equals 1. Not very far, right? It didn't take long, and the solution doesn't exist, right? You know, beyond 1, right? Okay? Now, if we were solving this for y as a function of time, like y of t, then this is also referred to as blow up in finite time, right? Blow up in finite time, right? Because all you gotta do if x was t instead, that you just gotta get out to t equals 1, and things blow up, and that's bad, right? In a model, right? That's not so good. And it looks, remember, this was like a very innocuous looking problem, right? This doesn't look like something crazy ought to happen, like blow up in finite time, right? And if we think about our Picard theorem, right, what do we have? F of x and y is y squared. That's continuous everywhere, right? Y squared is continuous for all x's and for all y's. So if you think about our rectangle that was up there, and then what's partial f, partial y? Just 2y. Also continuous everywhere, right? For all x's and for all y's, yeah? And so you get no hint at all from the differential equation that there could be some crazy blow up happening when you get, you know, anywhere, not very far, right? So here's 0, 1, and whew, you know, that's kind of crazy. So that's the difference between what can happen with nonlinear problems and with linear problems. You're not going to get, you may not see, you likely won't see in the equation where things could go wrong, and the initial condition would change where things could go wrong as well. So that's one of the reasons why linear first order initial value problems are so fantastic. You could try computing the phase plane if we want to do a nice big wrap up of lots of things that we have talked about. If you look at the slope field ideas, right? Things that we talked about when we did slope fields. For this guy, if I think about equilibrium solutions, well, does it have an equilibrium solution? We already talked about that, y equals 0, right? So that's this guy right here, right? Y equals 0, we can't cross that one. We like y prime equals y squared. That's awesome. What do you know about y squared? Always positive or 0, but certainly positive away from 0, okay, on either side. And therefore, what do we know about y? It's always increasing, right? So y increases up here and y increases down here, yeah? What else do we need to know then? We would want to know about y double prime. Well, if y prime is y squared, this prime means derivative with respect to x. So what is the derivative of y squared with respect to x? 2y prime, right? So that's 2y times what's y prime? Y squared. But what is y times y squared? Y cubed, right? And so what do I know, right? This guy is positive if y is positive, and negative if y is negative. And if this is positive, then what does that mean? The second derivative, positive, means y is concave up. And the second derivative, negative, means y is concave down. So solutions are increasing and concave down here, right? And increasing and concave up here. Yeah? And without a more careful look at the slope fields, right? So let's suppose that is 1 and that slope is 1, right? When y is 1, the slope would be 1. When y is 2, right? Let's call that 2. Then the slope would be 4, right? So that's more steep. Yeah? Does that make sense? And so when y is 3, the slope would be 9. You might get a sense from looking at the slope fields that things are going awry pretty quick, right? As far as growing fast. But that type of behavior where the solution doesn't exist for all x, the solution only exists here on the interval 0 to 1, right? So this solution exists for x in 0 to 1. You would have had no hint that that would have been the case just by looking at the differential equation. And that's why nonlinear equations, crazy things can happen, right? Linear equations, much more understood. Okay, so one last thing we're gonna do before we wrap up this section is just mention a little bit more about concentration problems. So that's section 1.4, first order linear ODEs, a classic example of those kinds of solutions are concentration problems. So let's talk about those for a sec. This isn't the concentration problem that you're having right now, which is paying attention to concentrate to on this topic, right? Okay, or maybe the concentration problem I'm having right now, paying attention to concentrate on delivering this topic. All right, so anyway, let's write down a classic differential equation for a concentration problem. I'm going to post something online that will help you out with this a little bit. Your book gives you an example of one concentration problem and talks a little bit about that. Let's write down this differential equation and we'll decipher it in a sec. So here's the basic form of a concentration problem. X prime is, and sorry, this is X is the what variable? Good, dependent variable. You know that just by me writing that down. Okay, now we don't know what any of these other things are, okay? FICI minus FO 1 over VX. What in the world is that? Okay? So how in the world is it even a linear first order initial value problem? Well, okay, it doesn't take too long to identify. Since we have identified the dependent variable, I can write that in standard form. If I write it in standard form, what do I want to do with this equation? Yeah, X is my dependent variable. What's my independent variable? Well, any letter other than X or one of the ones up here, but yeah, T is your typical classic because you're talking about things changing with time, right? Okay, and so that means how do I want to write this in standard form? Well, now X is in the role of Y, we can deal with that, and T is in the role of X, okay? So some of these guys may depend on T, okay? All right, so how would we write it? We would write it as X prime, right, of T, just to be clear. We would bring that piece across, right, plus F0, we'll talk about what that is, times 1 over V times X is equal to FICI, yeah? Now we're in this form, right? First derivative, stuff that can only depend on T, okay? This can depend only on T. My dependent variable X, my unknown, right? And similarly, this can only depend on t. Yeah? Okay. So my unknown function is x as a function of t. Okay? All right, now I'm going to erase this piece over here just to get it out of your way, because now we're using different letters. Okay. So what does this say, right? This says, different color. What does x of t stand for? X of t is the amount of a substance. The amount of a substance. That's what x is, amount, present at time t. Okay, so basically what does this say, right? X prime means the rate of change of amount, right, with respect to time, right? The rate of change of the amount with respect to time. What are the units of that kind of a thing, okay? That's one of the things you want to think about, right? The units here have to match the units here, which have to match the units there, okay? Now, what is this, right? Well, this is the subscripts I mean in, right? This is basically flow in minus flow out. Okay? So that's kind of the deal. The rate of change of the amount of something, right, in some modeling scenario is going to be, right, how much flows in minus how much flows out, right? That's kind of the deal. Okay, so let's define these other guys, okay? Fi, well, let's talk about what C is. C is concentration. Okay, so concentration has units of amount per volume, right? Okay, if you think about that, amount per volume, the concentration of something. How much is there based on how much 3D space is there, right? Okay, so concentration has units of amount per volume, right? So this guy has units of amount per, good, rate of change of amount with respect to time, so amount per time, yeah? So everything that goes into this equation, right, each one of these pieces have to have units of amount per time, right? Concentrations have units of amount per volume, right? So Ci is an input concentration. For our concentration problem, right? And Fi is a flow rate in, right, for how fast things are coming in, right? And so that, what would that have to have units of, right? So, so if concentration has units of amount per volume and the product has to have units of amount per time, what does the flow rate in have to have units of? Good. Volume per time. Because when I do volume per time, right? Volume is what's flowing in. It's a rate, so how much is coming in per time, times an amount per volume. What am I left with? An amount per time. Yes? Okay? Okay? So making sure your units match up will definitely help you with these problems. Okay, so what is the same thing? So Fi is an input, is a flow rate into the system. F0 is a flow rate out of the system. right? Flow, how fast things are flowing out. That also has units of volume per time, right? Okay. CI, input concentration, is often a constant. These flow rates could be constants or they could change with time, okay? And then what do I have right here, right? This, okay, X over V, well, that is concentration at any time t. The concentration at any time t is the amount at any time t divided by the volume, okay? At time t. The volume can also change, right? So it's just the exact same thing, FICI minus FOCO, or C heading out, C current, right? Okay? X is amount, V is volume, amount per volume times volume per time is amount per time. So that's the basis of a concentration problem. The rate of change of an amount with respect to time is the flow rate, is the how much is coming in minus how much is coming out, right? The rate at which something's coming in minus the rate at which it's coming out. Okay, so the volume, what is the volume at any time? Just to kind of also, so I just erased this, right? But if you were going to solve this problem, right, then you would set it up this way because this is the way the physics makes sense, right? And the understanding of what is happening. Then what would you do to solve it? You would write it in standard form by bringing that across and then identifying your P of T and your G of T, right? Because basically this is just X prime of T plus P of T X equals G of T, right? The P of T is F naught times 1 over V, right? And the G of T is, or F out, Fi times Ci. Yeah? Right, let me bring that guy across. Okay, and so we have our method for solving linear equations, right? Except now instead of y prime of x, it's x prime of t. And instead of p of x and g of p of x and g of x, it's well, p of t and g of t, right? Okay, so the other thing for more interesting problems, but this works in general, is that the volume at any time t is your initial volume plus, well, what? So if I add up from time 0 to time t, what's flowing in, volume per time, right, with respect to s, right? Volume per time times time gives me volume, yeah? Integration units. So this will come out as a function of t, and then I would subtract what's leaving from time 0 to time t, volume per time times time, this is integration with respect to time, I get out volume, yeah? And so this is the volume of your solution at time t. Now you might have some interesting problems where you need flow rates that are non-constant. They don't come up that often, but if you need it, this equation is definitely more versatile than the process in the book, okay? So what do you do with all of these concentration problems, right? You've got to identify what is the thing, pay attention to the units, right? Kilograms, right? That usually means amount, right? Right? Kilograms per gallon, right? There's a volume for you, right? Okay, gallon, okay? Anyway, pay attention to units to help you set these problems up, right? And then you're just looking at identifying what the input flow rate is, like if that's a constant, right? Well, obviously this equation still works if it's a constant, right? Because then you would just integrate a constant, yeah? And that would be nice and simple. For determining your guy, V, okay? And I don't think there's really much more I want to say. I'll post a little, little help sheet on all of these things and how to think about their units. But that's basically your setup for a concentration problem, right? Flow in minus flow out. Pay attention to units, that will help you decide what are in the F positions, right? What's the input concentration? And then this guy is your dependent variable, and this guy is what is your volume of your solution at time t, okay, which would change, right? Okay, so depending on whether you're asked for amount, if you're asked for amount, you're looking for x of t as a solution. If you're asked for concentration, you're looking for c of t, right? C of t is x of t over v of t, right? Okay. There's all kinds of problems that scientists, chemists, engineers would utilize that are concentration problems, and the nice thing about them is in this relatively general scenario here, right, where we can have these variable flow rates and things, you still end up with just a linear first order ODE, for which we know initial value problem will have a unique solution, provided all we do is just look at this guy and make sure they're continuous, right? Okay? Functions of t, and then we're in good shape, which is pretty awesome. We don't have to worry about crazy blow-ups, okay? Is there anything else I wanted to mention? I think there is, but I can't quite remember what it was. Oh, an initial condition, there it is. So that's the ODE. Then it's just a matter of deciding what your initial condition is. So you got to pay attention to the words, translate words into math. If they tell you the initial amount of something, right, then that means x at 0 is blah, right? If they tell you an initial concentration of something, that means c at 0 is something, right? And then depending on what it is you're solving for, you might have to manipulate to get the initial condition that you need for this problem. Yeah? Okay. I think you got it. I'll post something in files and see you soon.